Hi, everyone. Thank you for attending today's webcast, Thinking of Hot Water as a System. I'm Kanchan Swaroop. I'm with the Appliance Standards Awareness Project, and I'll be moderating this session. We'll start with our first speaker, Bob Staten. Bob taught solar energy for a decade at Cabrillo College and is the author of two books on solar energy. He's lived in an off-grid solar home for 20 years. And Bob will discuss a new method of passive freeze protection for flat plate thermosyphon solar thermal water heaters. Bob, take it away.
Well, thank you for the opportunity to present my idea today. Let me be clear about expectations here. What I'm giving you is a design principle for freeze protection system for solar thermosyphon systems. It's not a product, it's not a patent, it's an idea that also with a working example. But I believe this is an idea worth spreading, as they say in TED Talks. Thermosyphon systems are remarkably simple. If you look at the diagram here, you can see it's just a basic loop with a solar collector and a storage tank, and the basic design principle for that is you mount a tank above a flat plate solar collector. You plumb the top of the collector to the top of the tank, and you plumb the bottom of the collector to the bottom of the tank. It's simplicity itself. Thermosyphon systems operate when the sun shines on the collector and warms it up, and the warm water, I should say, rises into the elevated tank, and the coldest water at the bottom of the tank sinks down into the bottom of the collector, creating a circulation loop. The advantages of thermosyphon are many. They are completely automatic. They flow when the collector is warmer than the tank, and they stop when it's not. There are no complicated parts to fail. There's no heat exchanger or toxic fluids. No electricity is required. It's inexpensive, and it's simple enough to do yourself. Thermosyphon has a couple of disadvantages. One is that in the design, the tank must be above the collector in order for the warm water to rise into it. If you have a source of water and an open system, that is, the system is operating at the house pressure as part of the pressurized system, then you could have a problem with hard water creating scale inside the collector because you're circulating water, ordinary water, through the collector. And because it's a thermosyphon system, it has relatively slow circulation compared to a pump system. So there would be more heat loss, and it would be a little bit less efficient than a pump system. But of course, the big disadvantage with the thermosyphon system is its Achilles heel, which is freezing. It's an unfortunate property of water that it expands when it freezes, and the pressure on it can burst the pipes in the solar water heating collector. And a single cold night is enough to ruin your collector. So people have put in place various freeze protection solutions in order to prevent solar water heating systems from experiencing those broken pipes. A drain down system, a drain back system, antifreeze with a heat exchanger. But any of these create complications, so it's no longer simple and no longer cheap. So I went back to basics, and when I was teaching at Cabrillo College and explaining thermosyphon systems, I would clarify for my students that the basic idea that they have that warm water rises is actually not quite correct, because when you add heat to water, it doesn't acquire anti-gravity properties and cause it to go up. In actual fact, what happens is the warm water expands, becomes less dense, and the cold water, which hasn't expanded, is more dense. And so it's the cold water sinking that drives a thermosyphon system. And in a loop, when the cold water sinks, that lifts the warm water, creating the circulation loop that makes the thermosyphon work. But the basic principle is that cold water sinks because it is more dense. So my new solution works on that principle, which is to allow the cold water in the collector to sink. And you do that by adding a second loop to the thermosyphon system. You have the normal loop where the solar collector feeds water up to the storage tank, but you have a second loop with a heat source below the collector. In heating mode, the coldest water in the storage tank sinks into the solar collector, driving the warmer water up into the storage tank. So this is the normal thermosyphon heating mode. But when it's cold and the water in the collector is cold enough to sink, then it sinks down into a heat source, which then warms the water and then is carried back up into the collector. So by sinking into some sort of a heat source, it prevents the water in the collector from freezing, and the circulation brings the warm water back up to the collector and keeps the collector temperature high enough so that the water in it doesn't freeze. So if you want to put a heat source below a collector, the engineer might think that, well, the first thing you do is you create an active heater with a thermostat, and the thermostat turns on when the water gets cold. But you actually don't need that because the heating requirements here are pretty minimal. What you need to do is keep the temperature above 4 degrees C, which is the highest density point of water. And that's relatively easy to do. You can do it with ambient heating from a building, or you can do it with ground heat from a buried coil. So I want to be clear that this is not just a theory. This is my example of a solar water heating system that incorporates this. I acquired these solar panels secondhand, actually for free, because someone was removing them from their roof. They're copper plate collectors with copper pipes, very nice. A little bit aged, but they work just fine. I set them up with a normal thermosyphon system. In my case, they were on a hillside below the house. So I buried the pipes in the ground with a great deal of insulation and protection. And they rise about 17 vertical feet into a tank that's in the house. And that's the basic heating loop for the thermosyphon. And of course, I wanted to prevent this from freezing. So I added the lower freeze protection loop, which is a second loop of copper pipe plumbed into the same connections, but going down instead of up. And at the end of those circulation pipes, I buried a coil of copper pipe. I was fortunate enough to find 1-inch coiled copper to do this, so that I could run a long length of pipe without very many joints and be able to easily form it into a coil. And I buried this about 3 feet deep in the ground. And it works. I put this in service in September of 1999. I'm located in Northern California, and we experience a few freezing nights per year. We get in as low as the low 20s. And there'd be frost on the ground, but not on my collectors. And I had no burst pipes. And this system operates with literally zero maintenance. It just continues to operate and has operated for 20 years, providing me with hot water without freezing. So if you want to incorporate this design principle, there's several things you need to consider. First of all is the climate. I don't think I would try and do this in North Dakota because the heating requirements to keep the collector from freezing in the winter of North Dakota would probably be more than the heat you would get from the solar water heater, and wouldn't be worth it unless you wanted to drain the system during the winter months and operate it only in 3 seasons, which would be fine. The height difference matters. The greater the height difference, the higher the heat flow, but then of course you have longer pipe runs. The pipe diameter is significant. I tried to go with a 1-inch pipe so that to reduce the friction in the pipe. And you want to minimize the number of pipe joints and bends in the pipe because thermosyphon flow is rather gentle, and you don't want to create too many blocks to inhibit the flow. You want to insulate the pipes thoroughly. You don't want to lose heat, and you don't want to expose pipes to the freezing temperatures. You have to consider the rate of heat flow from your heat source that's below the collector. Sometimes that's hard to judge, and in my case, that was pretty much, I just made the biggest coil I could and put it in the ground. And you also have to consider the reliability of the heat source. So if it is an active system, then you have to worry about power outages and it not working. But in my case, burying a coil in the ground, well, that's a very reliable source of heat. The home example I give you is from 1913, showing a picture from the book by Ken Booty and John Perlman of Berlin of a solar water heating system installed in Southern California with a flat plate collector circulating water up into the tank stored in the attic. And the reason I mentioned 1913, because that was the year that they had a hard freeze in Southern California, and many of these systems that were in place at the time froze, and the pipes burst, and the company was running around trying to fix everyone and keep their customers happy. If, at the time, they had installed a second loop to carry the coldest water from the collector down into a heat exchanger down in the basement, for example, with a return line to bring the warm water back up to the collector, then they could have prevented those freezes. And of course, this technology was available at the time because it's the same principle that the heating system operates on. So it would have possibly changed the course of solar water heating in Southern California if they had had this design principle. The potential for this is on several different areas. Of course, do it yourself, as I have demonstrated, because it is so simple. It's just plumbing. And that also means it's inexpensive, so it could be done in developing countries. Remote locations are particularly advantageous because it doesn't require electricity. And of course, this could be incorporated into commercial products. There's a lot of thermosyphon water heating systems all over Europe. When I toured in Greece and Italy, I saw many of these on rooftops. Most of these are set up with a heat exchanger and a heat transfer fluid to prevent from freezing. But they could make them less expensive as an open system if they run a second set of pipes down into the living structure, which is, of course, generally below the collector if it's mounted on the roof. So these are just some of the ideas. I'm putting this idea out there because I think it has a lot of potential for application around the world. If you think in terms of where thermosyphon systems can operate today, normally you wouldn't want to put it in any place where you would have any freezing at all. So that limits the range to pretty much the tropics. But this idea, adding it on, expands the range of thermosyphon water heating systems into northern and southern latitudes that would normally not be suitable for it. So I think it has a lot of potential, and I'd like to see it get out there. So that's why I made this idea available in this forum. So thank you very much.